In order to balance chemical equations, we need to talk about this thing called polyatomic ions. So polyatomic ions are ions that contain multiple elements inside of them. Normally, you all are used to seeing ions look like this. They'll look like K plus, like potassium, right? Or calcium 2 plus, or chlorine 2 minus, right? They're a single element from the periodic table with a charge on them. However, polyatomic ions differ in that they have multiple elements. So here, nitrate is composed of nitrogen and oxygen. This polyatomic ion looks like this. It has a nitrogen and it's got 3 oxygens connected to it covalently. And that entire complex, the nitrogen with the oxygens on it, has a -1 charge. And that's why we call it a polyatomic ion, because it's composed of multiple atoms, so that's polyatomic. So multiple atoms. You're going to need to know polyatomic ions because they're going to be involved in balancing chemical equations, and we need to be able to recognize them because they're going to make it easier for you to balance if you're able to recognize the polyatomic ions. You're going to be given a list of polyatomic ions for your exams and quizzes and stuff. That's going to appear on the back of your periodic table. So like right here, you'll have this exact polyatomic ion chart to work with. So you don't need to memorize this, but you do need to get used to identifying them and seeing them for what they are when you are balancing chemical equations. So let's take a look at how to write chemicals with these polyatomic ions in them. So let's take a look at this one here. Students often get confused on this one because they see Na and they see the P and they assume that that's just phosphorus. So they might think that this is sodium phosphorus or something like that. But we've got an oxygen stuck to it. This here is right here in our polyatomic ion chart. It is a polyatomic ion. Here, actually, let me put the parentheses kind of here. The charge is outside of the parentheses. Okay. So this would be sodium phosphate. Another thing you'll notice is that if you go to your periodic table, there's no element called phosphate on here because it's not an element. It's not a single atom. It has multiple atoms. It's polyatomic, and thus it can only be found on your polyatomic ion chart. Now let's take a look at this next one, magnesium hydroxide. So magnesium is on the periodic table. It's right here. It's just a single element, so Mg. All right. And then hydroxide, you'd find it on your polyatomic ion chart. And hydroxide is located right here. So that's OH. So it'd be MgOH. I'm going to add the number 2 here. And I'm going to tell you why in just a little bit. So this number 2 here comes from the charge on our magnesium. So remember that magnesium, it's here in row 2. And thus it has a 2 plus charge on it. We learned this in topic 1, why it has a 2 plus charge on it. Our hydroxide is here. It has a -1 charge on it. So if there's no number written by the minus sign, it just means it has a 1. So when these 2 ions combine together to make a compound, an ionic compound, the charges need to balance each other out. So what this means is that if we have a 2 plus here, we're going to need a 2 minus here. And so it recruits another OH, which means that for every 1 magnesium, we have 2 OHs, because that's going to give us 2 minus 2, right? And minus 2 is equal to 0. So whenever you have an ionic compound that wants to form and wants its charges to equal out to 0, thus we see ourselves with 1 magnesium and 2 hydroxides in order to make that charge 0. I'd also recommend when you're writing these ions to put your polyatomic ions in parentheses. It's going to help you A, see them, and B, know where these little numbers are being applied. All right, now it's your turn. Let's see if you can name this chemical compound right here with a polyatomic ion in it. You will probably need to use your periodic table and your polyatomic ion chart on the screen. So if we look at the periodic table, this is calcium right here, so calcium. And CO3 is right here, so it's a carbonate, calcium carbonate. Now I'm going to ask you to do the same thing for the next one. It's a potassium carbonate, which tells us what elements we need from the periodic table and from our polyatomic ion chart. But I'm going to ask you to figure out the little numbers. So use this technique here to make sure that your numbers are balanced so that they come out to 0. You might have to add multiples of the potassium or the carbonate in order to make that happen. Let's take a look at the charges here. So potassium is right here on our periodic table. It's got a +1. Anything on this column has a +1. Anything here has a +2. We know that from topic 1. So potassium has a +1. Carbonate's over here. It's got a 2- charge on it. So CO3, and it's got a 2-. So in order to make these equal out to 0, we're going to need another potassium. And that will give us 2+ to equal out our 2-, which means that our formula for this is going to be 2 potassiums and 1 carbonate for that reason. Now there's a shortcut to remembering this. So if you ever get stuck and you can't quite remember that you need to add the charges up to 0 and you need to add multiples of them in order to do that, we have this thing called drop and swap. You'll notice that these subscripts here, this little thing, it comes from the opposite ion, right? The 2 is dictated by the 2 on the carbonate. And so what we say is that these numbers were dropped down from their charge and they swap over to the other ion. Let's take a look at one more example and let's apply the drop and swap. So let's do sodium, rolling with our alkali metals here, sulfate. Sodium is right here in group 1. So what charge does sodium have on it? It's going to have Na +1. Sulfate is in our polyatomic ion chart. What charge does it have on it? Oh, this is actually wrong. This is wrong. I'm sorry. This should be a 2-. Okay. Sorry. Sulfate has a 2- charge on it. So we're going to have SO4, 2-. Now we can apply drop and swap. We know that's going to be Na, and we're going to have SO4 here, and there's going to be some number belonging to the sodium and some number belonging to the sulfate. So we drop our numbers, they drop down, and they exchange positions. They swap positions. So we end up with Na2, SO4, 1. We don't need to write that down. So it would just be Na2, SO4. We know that this is true because in order for our charges to equal out, we need need 2 NAs to equal out the 2- charge on the sulfate. So +2, -2. So we'd have 2 sodiums. Another chemical process that we need to learn about when that's related to balancing equations is combustion energy. So the process of combustion is a chemical reaction, and this is the process of burning things. So if you think about a fire, right, what does a fire require to stay lit? How can you, there's a couple ways to put out a fire, right? What are some of the ways you put out a fire? One of those is obviously water, right? Another way is smothering it. So what you can do is you can actually take a fire and you can get rid of the oxygen and it will go out. So fires require oxygen to stay lit. So the first half of the equation, our reactant side, we're going to have some fuel molecule plus oxygen. What does fire produce? Think about what kind of chemicals fire gives off. What are those? If you can't think of them right off the top of your head, that's okay. I'm going to say in a minute, but just think about it for a minute. Okay, so they produce carbon dioxide, right? This is what we talk about greenhouse gases. Whenever we're burning things, we're concerned about carbon dioxide. And the one that most people don't remember is water vapor. Burning fire actually creates water vapor. And you're going to see this heat and light, right, from the fire as well. So these are our products. So our chemical reaction looks like this. We're going to have some fuel molecule plus O2 goes to CO2 plus H2O. So if you see an equation like this, this is combustion, and you are expected to know the products of this, and that it requires oxygen to continue combusting. So I'm going to show you some examples of balancing chemical equations. We're going to get to this. Don't forget your combustion thing. We're going to come back around to that. Don't forget your little numbers. We're going to come back around to that in your polyatomic ions. But for now, let's talk about how to balance equations and how we're going to get into that. So when we balance chemical equations, you'll notice that there are numbers in front of some of the compounds and molecules that are in a chemical equation. Here, we're assuming that there's a 1. So if there's nothing in front of a molecule, it's because we're assuming there's a 1 there. And these numbers are called coefficients. They indicate the proportions of the reactants to the products. So they're relating them to each other. And these are the ratios of them to each other. They let us compare the quantities of the molecules so that we can see how many are being made or formed in this process. This brings us to the law of conservation of mass, which tells us that the sum of the masses of the reactants that start in a chemical equation are equal to the sum of the masses of the products that end after the chemical reaction has taken place. So matter can neither be created nor destroyed. What's actually happening instead is everything is transformed. I really like this quote. Everything is transformed. So it just changes the way it looks, but nothing's ever disappearing or reappearing. So if we keep that in mind, we can say that when we balance chemical equations, nothing should ever disappear or reappear. It should just be in a different form. So what that means is that every atom in a balanced chemical equation should be the same on both sides. Here we've got carbon on both sides, and we've got hydrogen on both sides, and we've got nitrogen. So in this scenario, this equation is not balanced yet. We are going to balance it. We can look, and we've got a carbon, and we've got a carbon here. So we've got one carbon on both sides, so 1 and a 1. Technically, the carbons are balanced right now. Let's take a look at our hydrogens. We've got 4 hydrogens and 3 hydrogens, so that's 7 hydrogens here. And then we've got 1 hydrogen and 2, so that's 3 hydrogens here. The hydrogens are not balanced, so they need to be fixed. Nitrogen, we've got 1 and 1. Okay, so nitrogen is balanced, good. But we've got to fix this hydrogen scenario because right now we're seeing hydrogen disappearing. Technically, that's not possible. So let's work on balancing this hydrogen. What we need to do is we need to make sure that there's the same amount on both sides. Right now, we've got an odd number of hydrogen and an odd number. This number needs to go up. Clearly, it's not high enough. So is there any way that we can introduce a number here or here in order to make it so that there's 7 hydrogens total on the product side? So our reactants are going to be the things to the left of the arrow. That's our reactants, and our products are going to be to the right of the arrow. If you remember from our drop and swap rule, you'll remember that these little numbers cannot change. These are fixed. So we can't mess with those. The only numbers that we can mess with are the numbers in the front, which indicate how many molecules total we have. So now we can simply try different numbers here and see what we like. Right now, there's an implied 1 in front of these since there's no number. So let's try a 2 and see what happens. If we put a 2 here, that's going to give us the most bang for our buck, right? Because if we do 2 of these, 2 hydrogen 2s, we're going to have 4 hydrogens now. And so that puts us at 4 plus 1, that's 5 hydrogens. Okay. All right, we're getting closer, right? We're getting closer. We need 2 more to make that happen. If you decide to put a 2 here, that's only going to increase our hydrogen count by 1. That put us at 6. So that's probably not a good move. I would undo that. And instead, just continue to increase this hydrogen over here because we need to keep going up by 2. So that means we're going to have another hydrogen molecule. And then that puts us at 3 times 2 plus 1. This is the 1 right here, which gives us 7. Okay, so now we're balanced. So let's take a look at this reaction and this transformation and process and how it relates to balancing. So this was our final balanced chemical equation. So we're going to look at this CH4 and this NH3 and how it's transformed into the HCN and the hydrogen gas, the H2. So these are our starting molecules, the CH4 and the NH3. All right, so there's a carbon in the center, there's 4 hydrogens on the outside, there's a nitrogen, and there's 3 hydrogens. When we go to react these, they're forming something new. So this is our carbon here. So our carbon now, in its final form, was carbon, hydrogen, and a nitrogen. Excellent. Okay, so that was one of the products we made, right? And then the other thing that we made was hydrogen gas, which was H2. So we have a hydrogen connected to a hydrogen. Look at all these other hydrogens left over, right? And a hydrogen, and a hydrogen, hydrogen, hydrogen. So nothing is left over. If you ever find yourself with one of the hydrogens not being turned into a new molecule or something, that means it's not balanced. That means a hydrogen was left out of this picture. But in this scenario, every single atom was used to form something new, thus making this balanced right here. Oh, they aren't quite together, are they? It's a little different in 3D space. Anyways, that's the idea. So it's transformation of the atoms happening, and they are not being lost or created. Now, if this is a little confusing to you and you'd rather have some steps, that's totally fine. Or you can just guess and check. Whatever feels right for you, feel free to do it. So here's a method if you need to maybe try to keep some steps in your mind. The first thing that you want to do is you want to have the reactants and the products. You want to have the formulas written for those. And then you want to check whether the expression is balanced by counting the atoms on each side of the reaction. So that's going back to here, right? And counting and making sure that you have them balanced or not balanced and seeing what you need to fix. So assess the situation, see what needs to be fixed. Then what you want to do is balance an element that appears in only one reactant and one product first. Those are going to be easier to work with, and I'll show you why in here in just a minute. So you don't want to choose an element that appears in like 2 reactants or 2 products, or that's going to be a little confusing to work with. And then from there, you choose coefficients, whatever number you want, 1, 2, 3, 4, whatever it needs to be. It could be even higher, and balance the elements as needed. So that's that guess and check situation. So let's take a look at this. This first reaction is a combustion reaction. Let's first assess the situation and see what's imbalanced so we know what we need to fix. We've got 4 carbons over here. We've got 1 carbon over here. Okay, so that needs to be fixed. Hydrogen, we've got 8 hydrogens and 2 hydrogens. That also needs to be fixed. We've got 2 oxygens. Oh no, this isn't looking good. We got 3 oxygens over here, 3 oxygens. Okay, so everything needs to be fixed on this problem. So what do we start with, right? We're going to start with the easiest thing to fix. The easiest thing to fix here is going to be something that appears in the least amount of elements. So we've got carbon here and here. So it's only in 2, which is great. We've got hydrogen here and here. That's 2, that's great. We've got oxygen in 3 different molecules. So oxygen here is going to be the hardest to work with. So we're going to save that for last. So that was one of the rules that I gave you here. Balance an element that appears in only one reactant and product first, and save the other stuff for last. So let's get to work on the carbon first. You can choose carbon or hydrogen, it doesn't matter. Carbon has 4 on the reactant side at the beginning, so we're going to go ahead and just up this number to 4. Remember, we can only change the numbers in the front. Those are the only things we can mess with. We can't change the little subscripts. Those are fixed. So we put a 4 here, that's going to up our carbon to 4. Now this does also affect our oxygen, right? Because this is applied to the entire molecule. So we're seeing it come here as well. So now we've got 4 times 2, which is 8 oxygens plus this other one here. So now we're sitting at 9 oxygens. Okay. Again, let's ignore the oxygens. We're saving them for last, but don't forget to update your numbers. Let's fix the hydrogens now. So hydrogens, we've got 8 hydrogens on the reactant side. We've got 2 hydrogens on the product side. Clearly need to make the product side larger. So let's turn this into an 8 by putting a 4 in the front, because 4 times 2 is 8 hydrogens. Okay, carbons are balanced, hydrogens are balanced. Now let's take a look at the oxygens. Yikes, right? Let's update our numbers. I forgot to update my numbers. So we're sitting at 8 from the carbon dioxide, the CO2, and we're sitting at 4 from the water. So 8, 9, 10, 11, 12. So updating that number. 12 oxygens and 2 oxygens over here. Okay. Well, this actually isn't so hard now. We've got 2 even numbers. We've got a 2 and a 12. So if we want to make the left side look like the right side, we can simply put a 6 up here. So 6 times 2 is 12. Here, I'll do this, oxygens. So it doesn't look like that O is a 0. It's not an O. It still looks like a 0, doesn't it? Oxygen. There we go. All right. It's not a 0. Let's take a look at the second example now. The second example contains polyatomic ions, so we need to be wary of those. We have a carbonate ion here and a carbonate ion here. Whenever you see polyatomic ions, I'd highly advise you to just go ahead and put them in parentheses so that you spot them and you're recognizing them. Another thing that you shouldn't do with polyatomic ions is you shouldn't split them into their components if they appear the same on both sides of the equation. So because there's a CO3 over here and a CO3 over here, don't split them up into carbons and oxygens. It's only going to make your life harder. The only situation where you should split them up is if the carbonate is not the same on both sides. So if over here you had MgC plus NaOCl, right? And then over here you had Na2CO3, then you would have to split up the polyatomic ion, right? Because it's not here anymore, it's separate. So then we would have to consider the carbon separately and the oxygen separately. But this equation's a lot easier because the polyatomic ion is in the same form on both sides. So it's CO3 over here, CO3 over here. Don't need to split it up. Now let's take a look at balancing this. You want to make sure that you treat the carbonate as its own thing, and we're not going to split it up. So we've got magnesium. We've got 1 magnesium here. We've got 1 magnesium here. It's looking good. We've got 1 carbonate here. Still looking good. 1 carbonate here. Let's go to our sodiums. We've got 1 sodium here, 2 sodiums here. Oh, okay. We need to fix that. We've got 1 chlorine over here, and we've got 2 chlorines over here. That needs to be fixed. Okay. So here's where our changes need to happen. In our product side, the Na2, we've got more sodiums than we need. We've got more chlorines than we need. So that means we need to put an increased amount of NaCl's on the reactant side. So if we bump this up to 2, it's going to give us 2 sodiums, check. And the 2 is distributed to everything inside the molecule, right? It goes to the entire molecule. And so that gives us 2 chlorines. 2 chlorines. Excellent. Let's take a look at the next one. So here we have iron and oxygen gas forming an iron oxide compound. We want to count up our atoms first. We've got 1 iron on this side. We've got 2 irons on this side. Whoopsie daisy, that's imbalanced. We've got 2 oxygens here, and we've got 3 oxygens here. So something you'll notice that I think is another thing to take into account is whether you have odds and evens of things on each side. So this is a bit of a red flag for me because I've got a 2 and a 3 here. So if I had a 2 and a 4, I wouldn't worry about it. If I had a 3 and a 5, I probably wouldn't worry about it because the odds are easier to work with, or the evens together are easier to work with. But right now they're imbalanced, which means we're going to have to find a common multiple for these. So we need to turn them both into even numbers. They can't stay odd like this. So that sounds hard, so let's not do that right now. Let's go for something easier. Let's work on the irons. We've got 2 irons on the right. We need another one on the left, so we're just going to go ahead and put a 2 here. Irons are balanced now. 2. All right, we're done. We're done with that. Now let's take a look at our oxygens. We do have to balance this. If you decide to put a number here, a 2, like this, that's going to increase you to 4 oxygens, right? Which isn't 3. You're still 1 number off. This is the problem with the odds and evens. So what you want to do is you want to choose a multiple that's going to let you get this to an even number. So 3 times what number will get you to something even? And ideally a lower number is better. And in this case, it's pretty simple. 3 times 2 will get you to 6. So we're going to go ahead and put a 2 here. And that's going to get us to 6 oxygens. And now we can get this number to 6, right? Because 2 times one number is 6. 3. We're not done yet because this, by doing so, affected our iron as well, right? It goes to the entire molecule. So now we've got 4 irons here. Okay, so now our irons are imbalanced. So we've got to go back and update this number to 4 as well. So this is that guess and check process, right? Like as you are adding numbers, your elements and your atoms are going to change. And so you need to update your numbers as you're working. And now we're balanced. Now let's have you try this example here. We're going to have magnesium hydroxide and sodium chloride turn into magnesium chloride and sodium hydroxide. See if you can put numbers in the front to balance them out. So first things first, when we're solving this, we need to look at our different numbers of our ions and our elements here. Now remember polyatomic ions, right? This is a polyatomic ion. I would not split this up. I'd keep that in parentheses. Whenever you see them, just put them in parentheses. That way you'll know they're there. So magnesium, we've got 1 and 1 on both sides. It's balanced. Hydroxide's not. We've got 2 OHs on the reactant side, and we've got 1 OH on the product side. So we need to balance this. It's not balanced. Our chlorines are imbalanced too. We've got 2 and a 1. So I'm going to start with my hydroxides. Since there's 2 hydroxides here, that means we need 2 hydroxides here. That's going to update my sodiums now. Now I've got 2 NAs. I only have 1 Na over here. So let's go ahead and add a 2 here. Now let's continue to check things since as we're changing numbers, things update. So it's 2 Na. This goes to the whole molecule, right? So 2Cl, 2Cl. Okay, excellent. I think we're balanced now. We've got 2 OHs and 2 OHs. All right, so that's all you need to do for this one. Let's have you try the second example now with this combustion energy. The C2H4 plus O2 goes to CO2 plus H2O. So remember to see which elements are on both sides, and then you're going to want to start balancing the things that appear in the least amount of molecules first. So let's take a look here at which atoms are in which molecules. We've got carbon sitting here, carbon here. So it's only in 2. We've got a hydrogen here and a hydrogen here. It's only in 2. But our oxygen are in 3 different molecules, so save it for last. So let's start with our carbon. We've got 2 carbons on the reactant side, 1 carbon on the product side. So let's go ahead and update that. So now we'll have 2 carbons and 2 carbons. We'll come back to the oxygens last, right? We're saving them for last. Hydrogens, we've got 4 hydrogens here. We only have 2 in the product, so this needs to go up 2. That gives us 4 hydrogens here. Right, now, only now that that is done, let's look at our oxygens. All right, we have 2 oxygens on this side. We've got, remember this applies to our entire molecule, so we've got 4 oxygens here, plus 2 oxygens. That gives us 6 oxygens. Okay, so we need the left side to look like the right side now. In order to do that, we're gonna have to put a 3 here, and that will give us 6 oxygens. See if you can do this one now. We've got sodium phosphate plus magnesium chloride goes to sodium chloride and magnesium phosphate. When you're working with these, remember to identify your polyatomic ions. So I'm going to go ahead and put those in parentheses. This is also a polyatomic ion. It's already in parentheses, which is great. And remember to not split those up if they appear on both sides of the equation. It looks like we don't have any elements or ions that appear in more than 2 of our reactants or products, so we're good on leaving something for last. We've got 3 sodiums on this side. We've got 1 sodium on this side. The order in which you approach this does not matter. Whatever one you want to start with is totally fine. We've got 1 phosphate on this side. We've got 2 phosphates on this side. All right. We've got 1 magnesium here and 3 magnesiums here. All right, so I think everything, literally everything, has to be updated. 2 chlorines and 1 chlorine. So again, order does not matter. Just start adjusting things and update your numbers as you go. I'm going to start with sodium because it's just the first here. So 3, so that means we need a 3 here. Gives us 3 and 3. Phosphate, we've got a 1 here, we've got a 2 here, so we definitely need a 2 here. Now this changes our sodiums, right? So our sodiums now are at, this applies to our entire molecule, so 2 times 3 is 6, so now we've got 6 sodiums. So let's go back and fix the sodium now. It can't be 3 anymore, we need a 6. 6, all right. Let me update these numbers, 6Na and 6Cl. Oh, and there are 2 phosphates here. Sorry, I forgot to distribute it to the phosphate. All right. So our phosphates are looking good. They're balanced. Our sodiums are looking good. They're balanced. Magnesiums are still not balanced, and nor are our chlorines. We can see over here we've got 3 on this side, and a 6. Oh, that's perfect. That means if we put a 3 here, then we'll have a 3 and a 3 times 2, which is 6. So 6 chlorines and 3 magnesiums. So your final answer would be 2 Na3PO4 plus 3 magnesium Cl2 goes to 6 NaCl plus Mg3PO4 2. Now, if you found that a little challenging or you struggled to get a hold of it, don't worry. We have more problems on the homework for you to practice with. I think the more practice that you do this with, the easier it's going to get.